So now we can move to the sampling distribution of our OLS estimators in multiple regression. And so we're going to start off by looking at the expected value of our estimators. So remember, there's a couple of reasons why we're interested in this distribution, and that's because we want it to have certain properties, right? We want that unbiasedness and efficiency in terms of finite sample properties we'd like in our estimators. So we want the expectation of each of our beta hats to be equal to the true value. And then we want to calculate the variance. I mean, after we get this expected value, we want to calculate the variance to be able to compare our estimator to other estimators and see which one we like more. And then we also want to know the distribution so we can do hypothesis testing. So this is why we're doing this. We're not going to derive it the same way as we did in simple regression. We kind of saw how that worked. This is just going to be more algebra. So let's just state the assumptions, and then under what assumptions we're going to get an unbiased estimator for each of our beta hats. So the assumptions we need. So some of these are the same as simple regression. A couple of them are a little bit different, or one of them is a little bit different. So the first one we want is linear in parameters. So that's the same as simple regression, right? We just want the betas to enter that regression linearly. Doesn't mean that the x's have to be linear. We can have x squared. We can have the log of x. We can have the log of y. It just means that these parameters, it has to be linear in parameters. The second thing we're going to assume is random sampling, just like simple regression, random sampling. So we're assuming all the x's, so x1 to xk, as well as the y, are IID draws. So they're independent and identically distributed, and we're getting our sample from randomly. We're getting our sampling is random. Whew. Okay, the third one is going to be a little bit different than what we saw before. So before we needed some variation in x. We couldn't just have one value for our one independent variable. We're changing that assumption now to no perfect multicollinearity. And we'll have to talk about what that means in a second. I know it's a mouthful. No perfect multicollinearity. But let's put we need to talk about this. This is new. Our fourth assumption is going to be that one that is going to be very similar to the one we were making in simple regression about the relationship between our u and our x's. And so now the expectation of u conditional on all the x's is assumed to equal 0. And again, this is one that anything that's in that error term that's correlated with our x and that influences y is going to cause this to fail. And we're going to kind of explore that through something called omitted variable bias. But let's take a few minutes and talk about, so 3 is different than simple regression. Let's see what it means. I mean, essentially it means that one of our x's is not a linear combination of the other x's. But let's kind of expand on that a little bit to make sure and look at maybe an example so we know what that means. So no perfect multicollinearity was that new assumption. No perfect multicollinearity. So let's talk a bit about what that means. It means that independent variables can be correlated, but not perfectly. talk about what happens when they're highly correlated when we get to the variance, but our assumption here is that they're not perfectly correlated, or that one independent variable is not a linear combination of the others. Oh, that was really bad. Others here. That's supposed to say others down there. Of at least two of the others, right? Doesn't have to be all of the others, just a couple of them. Two or more, I guess. Okay, so that's what this means. So let's look at an example where this might be violated, because maybe that will help kind of piece together what exactly it's saying or when it's going to fail. So for example, for perfect multicollinearity, let's imagine there's two parties running for some congressional seat in the US. And our dependent variable is the percent that voted for party A. Or the person that represents party A is probably a better way to think about it. And as our independent variables, we're interested in expenditure. So this is expenditure, like campaign expenditure by party A plus beta 2 expend B plus beta 3, and let's say we include total expenditure. I guess I should be using different colors, maybe it'll show up a little bit better. So this is expenditure by party B. So political party B is what I mean by that. And total expenditure is expend A plus expend B. So total expenditures by both parties in this congressional election. Well, this is going to violate that perfect multicollinearity. So it violates that assumption 3, because x3 here is equal to x1 plus x2. So this is an example where we wouldn't be able to run this regression. In terms of if we try to do it in Stata, we'd get an error, or really what would happen in Stata, just automatically drop one of these variables to eliminate this perfect collinearity between these variables. So it just maybe drop this one or this one or this one. So usually when you're doing this, it's going to be a mistake. You don't mean to have perfect multicollinearity. You just made a quick mistake. But this is what the assumption's saying. One of our x's, in this case, any of them, I guess, but this total expenditure is a linear combination, in this case, just adding these two other x's up. So that violates that assumption. So under these assumptions, now that we know what perfect multicollinearity means, under assumptions, the first one, that linear in parameters, second one is random sampling, the third one was that one we just discussed, no perfect multicollinearity. And the fourth one being that big assumption we've been talking about, that error term is uncorrelated. The expected value, it's mean independent. The error term is mean independent of all these other independent, or all the independent variables. Remember, that's the big one that was failing all the time in simple regression. So under these assumptions, the expectation of beta hat j, so any one of our k independent variables, is equal to the true value of that effect, the true value of the parameter. And I don't know if I should put for all, but for j equals 1 to k. So for all of these, all the slope parameters and the intercept as well. Under these assumptions, we have unbiased estimators. Again, we're making a big assumption with that fourth assumption. We still are.